So, in this lecture, we will be talking about outliers removal techniques in machine learning. Generally, well, I'll put this way, there are two types of the techniques. The first one will be the one where we call the outlier diagnostics, which are the techniques where you want to remove the outliers, and it's like checking and remove, sorry. You check and then you remove. However, there's another types of the techniques where you may or may not try to remove those outliers, but you tend to use your entire data, okay, to learn a robust, um, maybe a robust linear regression, or maybe robust just any estimation. So the second one will be more about how can we make the machine learning more robust given all the data. But yes, some of these techniques, such as the first technique and the last one, will not only try to come up with a more robust regression, but also try to remove the outliers. So yes, the difference between these two is like the first one is like you try to detect and then remove. But the second one is like you may or may not want to remove it, but it's like some algorithm may detect, remove, and reconstruct, but others maybe just try to reconstruct the output despite outlier. So the key is more like the first one you just remove it, but the second one you try to come up with the new estimation that is more robust than the techniques that people normally use. Yeah. So the first type of technique, like the outliers technique, you can think of it as like an additional block to your data pipeline. For example, you may be having like a data processing, and then you may apply this technique to remove the outliers. And then after you remove the outliers, then you may apply, maybe you give these data to some machine learning, like linear regression or something. But the second one, so I'll put it better, like this one. Okay, sorry, I'll just go back to the one at the top and put it like in a better way. It's like you have data processing and you do remove outliers, and then you call maybe or maybe train other machine learning that is like a normal one. It does not need to be like a robust method. But your second type will be that you have your data and you may or may not remove it. I mean, the outliers. But then your ML method is the robust method. So the difference is like for the first types, the outlier diagnostic is like a toolbox that maybe you add before you perform any learning in machine learning or processing your data. But for the second type, that was the robust regression, you are making your machine learning more robust. That's the difference between these two techniques. But I think before we go towards to how these two techniques are working, like in detail, maybe we should define what the outliers in our data look like and what types of outliers that we are considering. So the type of outliers that we are considering in this lecture and perhaps also including in your lab sessions, are the outliers in your training data. Because the training data are the data set that you would use in training your model. Therefore, the model performance will heavily depend on these data. Okay. And secondly, the types of outliers. There are actually two types that we will cover in this lecture. The first one will be the type of outliers in our input feature. And usually we will call it the bad leverage point. For the second types, we call it outliers. Just outliers. Or measurement outliers. Or sometimes in some slides, they may call it like high influential. Sorry. Points. So, sorry, just maybe it's just high influence point. Yes, maybe not sure, just high influence. Um, and also, I'll put this way. If we have the outliers, maybe the simpler case is to consider the outliers in measurements, which is like the second type. These outliers may be easy to understand if we think about the fact that if in our task that we are considering are just classification or regression, or classification, the outliers, maybe something that makes your prediction y hat different from the ground truth, maybe y or just y0. Yep. And the thing is, for regression task and classification task, the outlier could be easily diagnosed because, let's say, if your regression output is only like a scalar, then the outliers is just like a scalar value. In this case, outliers will be actually, if you ask me, if whether or not the outliers in this lecture that we are discussing the same as the measurement noise, the answer is I'll put this way: it can be the measurement noise in our training label or training target, but that noise impact our learned model like the beta, and therefore when we compute the error with respect to maybe measurements. However, the outliers will be the one that kind of like making this out, the error between the two very big. That's when we call it outliers. This could mean that suppose that the measurement noise is Gaussian. We know that Gaussian noise is not big. But what if in our data collection process, some of our training data may be having labeled inaccurately, such as human error. Then these errors will stay with the measurements that we use in training. And therefore, as we use this training data, we will get y hat that is inaccurate in a bad way, like very inaccurate, like the error is very high, even though our reference may be noisy. So that is the meaning of the outliers. Okay, any question? 3, 2,
So far, no.
sorry?
No.
No? Okay. Okay. Then, yes, that's the meaning of the outliers in measurement. And in fact, there are example here. But what I may not like about this example is because it can be very confusing. As in, we know that outliers can happen in our measurements, like inaccurate labeling, but also our inputs can have outliers as well. For example, if we may be using images taken from cameras as our input features, but the camera sensors may be not 100% working perfectly, then what we will have is that maybe some of the pixel in the images may be having something like a black or dark color pixels. Then those features will be inaccurate. So that's just an example of how the input features may not be 100%, and therefore they can also be the bad leverage as well. But again, these bad leverage also in input features are those samples of the input that deviate or behave totally different from the other input samples. And notice that I'm calling them input samples instead of the input features. We'll go into detail. Maybe we do it right now. Okay, I'll skip a little bit and we'll come back to these later. Okay, let us look at this one. What I was trying to say about this, um, I think if we understand this, it will be simpler. Okay, let's just put all of that together. Okay, now we're going to the input, like input outliers or bad leverage. Okay, because I think this notation could be really confusing. Okay, now it's input outliers, or what we would call in this lecture the bad leverage. If you can remember from last time where we want to use the linear regression to maybe estimate a value, and then our training samples, maybe we have m samples for the measurements, and therefore our input should also have like m samples as well, where n here is the feature of our input. Like as I said, if this is like, if x is images, right, we may be having m images for training, and n is probably equal to 256 square if our image size is 256 square. It's a feature dimension. When we say that our input is a bad leverage, it means that that particular samples in the training set is behaving out of the norm. So it has nothing to do with the feature dimension. That is something to keep in mind. And actually, in the notation that I use throughout these slides, um, I'll use the superscript to denote the sample's index and the subscript to denote the feature dimension. So in this case, for example, if I have like m images, let's say 1000 images for my training, then this will be like 1000 um, number of rows and maybe 256 square for the number of features. So it can be R 1000 times 256 square, something like that. And if we say that our samples has bad leverage, it's usually mean that some of these samples among these 1000 samples are the bad samples. They are the one that deviate from the other samples or maybe the general trends of other samples. Yes, so that's what we mean when we talk about the outliers. So it's the error along the sample's dimension. On the other words, if we say that, okay, what if we come up with a technique to remove these input outliers? Let's say we will remove three samples that are outliers, then that means that maybe we would say we remove xj equal to 10, xj equal to, sorry, j equal to 20, and xj equal to 30. This means that if we remove these three out, this could mean that we may be sorting for the rows 10, row 20, and row 30. And at the end, after we remove this 10, 20, and 30, we may be having x, actually we will be having x that is like of the size 1000 minus 3 times 256 squared. So that's what it meant when we talking about removing outliers and the outliers in the input features. Yes, it's just a sample based outliers. We are not doing anything with the features at the moment. Okay, shall we move on? Okay, all right. This is an example, like visually, what it's like if we have outliers in our training data. The thing is that, okay, in this example, it is very clear that maybe the red points here are the outliers. But what I find could be confusing, but in this slides, they just try to send you a very strong message that, outliers could be something that came from measurements, maybe a bad labeling because they all having low value all of a sudden compared to its peers. It is like up here. But also, alternatively, this bad sample could be the bad sample due to the inaccurate x value as well. Because, for example, if we keep plotting this line, maybe they're supposed to be somewhere that is at the very high value of x. That would make the correct map with the measurement wise. So when you have the inaccurate x like this, actually there are is like the inaccurateness or maybe something that we think that could be wrong may not necessarily just be the value of x, but it could also be the fact that maybe our assumption about the linearity between x and y is wrong as well. But in these slides, we will be considering the outliers removal in the linear regression system. Therefore, we can say that probably the mapping is not wrong, but maybe it's just the value of x and y. So another thing that I would point out here is that all these techniques are for linear regression. Yeah, that's it. Okay. Um, this is another example where maybe the tendency between, I mean, the outliers that's showing here is kind of obvious that, well, we have continuous x value, and therefore this y probably give like they are outliers. But what happens if these are outliers and it happens that we use this data to train our linear regression? What would happen is that we maybe end up with a linear mapping such as this one that was somewhat maybe pulled up by these outlier samples, when in fact if we can remove these outliers, maybe the mapping should be something that is look like this red line. So yes, that's kind of like the initial idea why people may be considering remove them and use the rest of the data to re-estimate the parameters in the linear regression. Yeah, so that's what it is. Um, this is just another example of the maybe inaccurate input features or the leverage points. And as I mentioned before, this is like, okay, this is maybe a good example of the fact that in this case, we are considering that the relationship between x and y is supposed to be linear. That is, the x is input here, this one is input, and y is this one. Thing is, if it's truly linear, then of course these samples are inaccurate. If the relationship is truly linear, so we can use the fact that the relationship between x and y is supposed to be linear to detect these outliers. Mm-hmm. Because if it's not linear, if we cannot make this assumption, right, about the linearity, possibly one can say that, fitting this line is not bad as well. It's possible, but it's just that when we say that everything has to be linear, therefore you can use the linearity to remove those red dots out of the training samples. And when we say we remove them, that means that, okay, let's go back to these slides where I first explained the J sample things. Okay, let's say if I want to, okay, if I can identify that X superscript 2, which is like the second sample, are the bad leverage. What I have to do is that, okay, I remove this xj equal to 2, but also that means I have to remove yj equal to 2 that is associating with x as well. Or maybe, if I have like the 999 sample, which is probably around here, if I have 1000 sample, then I have to remove this one and including the one that was like the measurements corresponding to it. So when we say we remove the outliers, whether or not it is like a leverage in X or the outliers in measurements, when we say we remove them, that means actually we remove the pair of the input and the outputs. Or on the other words, maybe we say we remove the J sample. So that means we remove these pair. Yeah, so that's it. All right, shall we move on? Okay, thank you. All right, okay. So let's recap a little bit about the linear regression system that we've learned from the previous lecture. So initially we have X here that is like the input features that has J samples. And let's say that if this Y and X here are the training, right? So we have M training samples. And then if we assume that x and y are supposed to have linear relationship, therefore we can regress or maybe forecast the value of y by using this linear model. So we have to estimate beta y from solving this least square error minimization. Then we get this beta. Sometimes we denote it as the beta least square or subscript with the ls. After we have this beta, then we can use the beta ls with our input x, which could be our testing, and we will get something like a y hat testing. That's supposed to be like a predicting value of our target measurements in the testing phase. Yes. And just to recap a little, uh, actually, one can solve for this beta by simply maybe taking the gradients and doing the matrix inversion, and then we will get the least square solution like this, which is just like we have to perform like a pseudo inverse, multiply with x and multiply with the measurements y. And please denote that this entire thing, like the entire data that we use to compute the beta ls here, they are all training samples. Yes, and probably in last week we talked about what could be the size of x, like the number of measurements that will guarantee that we can solve for beta and get the consistent results. Yeah, that is like another thing, but I wouldn't talk about here. In this presentation, we will assume that whatever x we have, it's a full rank, and we can uniquely find a linear solution.